Today we'll be doing a 1984 physics free response. Two satellites of masses little m and 3m, respectively, are in the same circular orbit around the Earth's center, as shown in the diagram above. The Earth has mass, capital M, and radius, capital R. In this orbit, which has a radius of 2r, the satellites initially move with the same orbital speed v initial, but in opposite directions. Part A states calculate the orbital speed v initial of the satellites in terms of capital G, capital M, and capital R. So in order to do this, we use previous knowledge that the centripetal force is equal to the gravitational force. This contains velocity, and using all of the other knowns, we can calculate our velocity. So the centripetal force is m, the mass of the satellites, v initial, r, it's m times v initial squared divided by r. We're doing the little satellite first, is equal to capital M of Earth, little m, g over r squared. In this case, the r will be the radius of the orbit, so that is 2r. Squared. Okay, and then using this, we just solve for v initial. V initial is equal to square root of mg all over 2r initial. And that is through simple algebra, and we figured out part A, which is the velocity using capital G, M, and R. Now for part B, which asks us, assume that the satellites collide and stick together. In terms of v initial, find the speed v of the combination immediately after the collision. So for this, we'll go on to angular momentum, the conservation of angular momentum. So the initial angular momentum will equal the final angular momentum, negative m v initial r is equal to 3m v initial r. No, these two added will give us the final, which is add both of the masses, which is 4m v. This is what we're looking for, r. The r stays the same. We can cross out the r's. We can cross out the m's. And then we simply get negative 2m v initial equals, equals 4m v. We solve out and we get that v is equal to 1/2 v initial. This is by the conservation of angular momentum. The final part, part C, asks us calculate the total mechanical energy of the system immediately after the collision in terms of G. So these are what we're allowed to use. G, little m, capital M, which is the mass of the Earth, and RE, which is the radius of the Earth. So if we want to calculate the total mechanical energy, we know that the formula is equal to the change in kinetic plus the change in potential plus the work that's done, or the internal energy. So this is what we're solving for, our mechanical energy, which is equal to it's equal to the change in kinetic, which is 1/2 m v initial squared plus 1/2 mv initial squared, that's the change in kinetic, minus 1/2 m1 plus m2 times 1/2 v initial squared. So taking that formula up here, we get that the change in mechanical energy is equal to 2m v initial squared, just by adding those up, minus 1/2 4m 1/4 v initial squared, and when we add that all up, we get 3m v initial squared. And that is the total mechanical energy that's used when the satellites collide. And that's all.